Okay, let's get started with a little bit of review, just 1 minute. We have introduced the gradient already last time, and we have seen that it allows us to write things like in single variable calculus. The linearization of a function of several variables is the function at some point, and then we have some correction term, and the gradient of f plays the role of the derivative. Also here, the chain rule looks exactly like the chain rule in one dimension. It's just that the gradient of f is now the derivative, and it's the higher dimensional version of the derivative, and the derivative of r, of the curve, that's the velocity. So these are two places where the gradient already appeared. And let me just tell you here, a gradient of f plays the role of the derivative. That's the derivative. So that's the derivative of a function of several variables. We will see other derivatives later, but that's the first important derivative, the gradient. And it gives us a vector. The gradient is not only an algebraic construct, like here it is a geometric object, it's a vector which is perpendicular to the level curve or level surface. Let's just formulate this. This is called the gradient theorem. So, theorem. Let me just formulate it in 2 dimensions first and then in 3 dimensions. The gradient is perpendicular to the level curve and let's just put it at x0, y0, so that's f of x naught, y naught. So the picture is like that. So we have a x and y, and we have the level curves. Think about this as heights for a mountain. And what we have is, say, this is the point x naught, y naught. The picture is that the gradient is perpendicular here. So this is the gradient of f. Actually, if the we will just see, this is not a mountain, this is actually something where you go up here. We will just see then afterwards in which direction the gradient goes. But the first fact is that the gradient is perpendicular to the level curve. Let me just prove you that. It's a beautiful argument. It's a proof. If r of t parameterizes the curve so we have this curve here, and this is r of t, so we have r of t which parameterizes this curve. Then what we have is that the key is to look at the following thing. What is d over dt of f of r of t? So that's an interesting thing which you can think about. What is that? F of r of t, if you look at f of r of t, if you go along the curve, we walk along the curve where the function is constant, what is the rate of change? So it doesn't change, right? Because f of r of t is equal to constant, that's equal to c by definition, so that's equal to 0. And now we use the chain rule. That's one reason why we have introduced the chain rule. We have that, so the gradient of f of r of t times r prime t is equal to 0. So that means that this is r prime. So this means this gradient is perpendicular to this r prime, but r prime is tangent. So we are perpendicular to a tangent, and that means the gradient is perpendicular to the level surface. Okay, let's just also formulate it in 3 dimensions. There is also a 3-dimensional version to it. If we have a function of 3 variables, then the gradient now a point is given, right? We have a point here given, x naught, y naught, z naught on this level surface is perpendicular to fx, y, z is equal to c to this level surface containing the point x naught, y naught, z naught. So it's exactly the same statement than before, but now we are in 3 dimensions. So the picture is like that. This is a level surface, and we have here the gradient of f, and this gradient of f is perpendicular to that surface. And the proof is exactly the same, except that we have now to choose different curves. Let's take one curve. So the same proof, r of t, a curve on this level surface, and then we do the same construction. So we have d over dt f of r of t, so that's the gradient of f of r of t times r prime of t. That's equal to 0 because that is constant c, and the derivative of a constant is 0. So we see again the gradient has to be perpendicular to that level, to that velocity vector. But we can choose any curve here through, and so that the gradient is perpendicular to any of these tangent vectors here. So that's the gradient theorem. Okay, let's look at a few examples. This is the example we have seen first, right? The case of a plane. So now we have this plane. It's an infinite plane, but I just draw part of it. And the gradient, what is the gradient of that function? So that's this vector, and this is the vector we have always called n. Remember when we looked at planes, and so this is n. This is the gradient of f. So this is a special case, and another special case is we have fx, y, z is equal to x squared plus y squared plus c squared is equal. Let's look at the level surface. This is equal to 3. So this is a sphere of radius square root of 3, and let's take the point 1, 1, 1. just shows a simple point here. What is the gradient? And so this gradient is, you see, it's actually just parallel to that vector here, which goes from the origin to the point. Let's look at also a single variable, a 2-variable case. fxy is equal to maybe x squared plus y squared. So what we have here is a curve which is a circle, and then the gradient of f is now a vector with 2 components. And if we compute this, maybe we compute it at the point 2, 1 equal to 5. So this is the square root of 5, and this is the point 2, 1. So in that case, when we take a 2, 1, so this is equal to 4, 2. So the gradient is just 4, 2 here, and it's perpendicular to the circle. So in 2 dimensions, important, the gradient is 2-dimensional, right? There are 2 components. In 3 dimensions, the gradient has 3 components. And so these are examples in 3 dimensions. This is an example in 2 dimensions. Okay, let's start with a concrete example. We have a surface like x squared over 4 plus y squared over 9 plus c squared over 16 is equal to 1. So this is a nice surface, ellipsoid, and we want to compute we want to compute the, so let's maybe make it 3 here, so to make it easier. And the problem is the following: find the tangent at the point x naught, y naught, z naught is equal to 2, 3, 4. So we have the point 2, 3, 4 here maybe. Now, so that's a problem which you could do with we could do with linearization, but that's nonsense. It's just much more work. What we do is we just compute the gradient. We compute the gradient at that point, and that gives us just the ABC components of the plane. Right? We are looking for this plane here, which is perpendicular to this ABC. So what we do is we just compute the gradient. Just compute the gradient of f. So this is f. The gradient of f is equal to 2x fourth, 2y ninth, and 2z 16. And at the point, we also evaluated at the point 2, 3, 4. So this is equal to 1. This is 6 ninths, and 4. This is 1/2. Actually, we can write this also as 2/3. So this is 1, 2/3, and 1/2. So that's a concrete vector here, and these are our coefficients A, B, C. Now, if we have the coefficients A, B, C, we can immediately write down the plane. So the plane is just ax plus by plus c is equal to d. And we have the ABC already, so that's x plus 2/3 y plus 1/2 z. And now the question is, how do we get the constant d? And but we have a point on that plane, right? A point 2, and then 3, which is 2 plus 4, and then plus 2 is 6. So this is equal to 6. That's the answer. That's how we compute tangent planes. For tangent lines, it works exactly the same way. Say we have a curve like that: x squared minus y squared is equal to 3. And again, let's just assume we have the point 2, 1. So here, so this curve passes through square root of 3 here. So it's got something like that. It's a hyperbola, another hyperbola. These are hyperbolas. And we want to compute the tangent line here. We want to find the equation for this line here. So we would be tempted to compute the slope, etc., and kind of fiddle around with a line equation, but it's much easier. So what we do is we find, this is f, find the gradient of f is equal to 2x minus 2y. The gradient of f at 2, 1 is equal to 4 minus 2. And we can immediately write down the equation. So this is now AB. So the line has the equation 4x minus 2y is equal to constant. And the constant we get by just plugging in the point 2, 1. So 2, 1 gives us 8 minus 2 is 6. Voila. That's the equation of the tangent line. It's so fast. You can, for any function like that, you can just find immediately this tangent. So this is the vector which we have just computed, which is 4 minus 2. Actually, it's going in the other direction. It's going there. 4 minus 2 is going here. And we will just look at this problem of direction when we look at directional derivative. That's the last section. Okay. So the directional derivative is just a definition. What we define is if you have a direction v, we look at the gradient of f. So that's at some point x. that's x and then times v. So that's the v is the direction. The unit vector, and del nabla is of course the gradient. So what does that mean? Let's look at examples. So let's take fxy is equal to maybe x squared plus y squared, and let's look at v is equal to 3/5, 4/5. That's a direction. And let's just take the point maybe 2, 1. So x naught, y naught is equal to 2, 1. So the directional derivative of v at f at 2, 1, what's that? So that's the gradient. You have first to compute the gradient, which is 2. So the gradient is equal to 2x, 2y. So 2x, 2y is 4, 4, 2. We have already seen this gradient. And we dot it with that unit vector here, 3/5, 4/5. So this is 12/5 plus 8/5. This is 20/5, which is 4. So what does that mean? In this case we have a x squared plus y squared, which gives us circles as level curves. And what we have is computed at that point 2, 1 here. We have computed the directional derivative in the direction 3, 4 over 5. So that's about like that, a little bit like that. So that's v. So what we have computed here is, if you look at the chain rule, you kind of see it better. If you kind of move in that, if you move in that direction, we actually have here just the rate of change of f when we go in that direction. So if that is a unit velocity vector, then this is just the rate of change. This means we are going up here. When we go in this direction, we are going up. Another example, important example is, let's just take, let's just write it here. So another example. So that would be maybe if v is equal to 1, 0. That's example A. Example B. If v is equal to 1, 0, what's the directional derivative here? So that's fx, fy, dotted with 1, 0. And you see it's just the fx. So the directional derivative, when we go in that direction here, that would be here at this point. If you take 1, 0, or here 1, 0, we can do it at any point. This is actually just the mean. This is the meaning of fx. Fx is a directional derivative. So this is a slope. So this directional derivative. This is a slope in the direction, like that, direction. So this is really the most important case, and it's the foundation of machine learning, of anything fancy, is when we are going in the direction of the gradient. So that's the important special case. If v is the direction of the gradient. So let's see what happens with the directional derivative. So we compute dvf. So what that is by definition, it's the gradient of f dotted with that gradient of f over. Now we have the dot product of the gradient of f with gradient of f. That's the gradient of f squared over the gradient of f. So that's the length of the gradient of f. That's a very important case. it tells us that if we go in the direction of the gradient, we are going up. In some sense, angel stands upwards. Now it's extremely important because you want to optimize things. When you have a situation like that, you have a landscape where you want to learn something, you have a goal to reach the best possible situation, and you are at some point, and this can be very high dimensional space of lots of parameters, and you want to learn, you want to find the best possible thing. What you do is you just go in the direction of the gradient. So the gradient is going here and we are going up. And if you do that, eventually you will end up on a local maximum. And that's something we are going to look at next time. We look at the case, what happens when the directional derivative is 0. And that will be in all directions. And that's the case when the gradient is equal to 0. And that's the topic for the next week.